Hi, welcome to Send to Print. At first glance, this might look like something you wouldn't want to touch, but for many people, spiky sensory toys are surprisingly satisfying to play with. Those little spikes create a unique tactile feeling that keeps your hands busy and can be surprisingly relaxing. It may look complicated, but in Fusion, you can build a spiky sensor toy like this in just a few simple steps and keep the whole thing parametric, including the spike feel. Change one value, and you can go from a low pain version to something much more intense. All right, let's dive right in. First, let's take a look at the design. Let's start by defining a few key parameters, including the cylinder's diameter and height. You may have noticed that the spikes are arranged in multiple layers. Each layer contains one ring of spikes, and the distance between layers is called the layer height. The whole fidget is built by stacking multiple layers. We'll start by entering the key dimensions into the parameter table. Think of it as your control panel for the whole model. This will make everything super easy to adjust later. Click the little plus icon to add our first parameter, diameter, and set it to 18 millimeters. I'll skip ahead here instead of showing every entry one by one. We've defined diameter and height as the cylinder's overall dimensions. We also need a layer count. It's calculated with this formula. This assumes the spike width and height are roughly similar. Finally, we'll calculate the exact layer height by dividing the total height by the number of layers. Before moving on, let's take a closer look at one layer of spikes. Each layer has 8 spikes. Working directly on a curved surface would be tricky, so I'll build the spikes on an octagonal prism instead. On each side face, I'll create a small quadrilateral and loft it into a spike. All right, let's start modeling. Right-click the root component in the browser and select New Component. Let's name it Spiky Sensory Fidget. I'll start with a sketch on the XY plane. Create an inscribed polygon with a radius equal to diameter divided by 2, and set the number of sides to 8. Check if it is fully defined here, the small lock icon. Finish the sketch and rename it to Octagon. Hit E to extrude. Set the extrusion height to the layer height parameter. This is one unit layer. The full fidget is made up of multiple unit layers. Next, we'll model the first spike. Create a new sketch on the XZ plane. Press P to project this face into the sketch. Let's hide the bodies for now. Press L and draw the first spike profile. From the side, it looks like a triangle. Since the print direction is along the Z axis, we'll set this angle to 45 degrees to avoid a steep overhang. Here's the interesting part. The spike height directly controls how this feels. To make that tactile feel parametric, go to the Modify menu and open Change Parameters. Add a new parameter called Spike Height. It controls the spike height and how intense the texture feels. For now, I'll set it to 4 millimeters. Press D and set this height to the spike height parameter we just created. Now everything looks fully defined. Okay, let's finish the sketch and rename it Spike. Next, let's sketch the base of the spikes. This sketch is created on the side face of the prism, but it only covers part of the face. Create a new sketch on this face. Press L and connect these midpoints. Finish the sketch and rename it Spike Bottom. Next, go to the Create menu and choose Loft. Loft the quadrilateral on the prism face to the point on the outside. That gives us our first spike. Luckily, we don't have to create all 8 spikes one by one. We'll use circular pattern to create a full ring of spikes. For Object, choose Features, select the Loft feature from the timeline, and use the Z axis. Set the quantity to 8. And now we have the first layer of spikes. Next, we'll create another layer. Since the spikes are staggered, we can't just copy this layer directly. I'll use rectangular pattern on this body. The direction is still the Z axis. Set the distribution type to spacing. Set the quantity to 2 Set the distance to layer height divided by 2. Right now, the 2 layers are aligned. We need to rotate the upper layer so the spikes are staggered. Press M and rotate the upper layer. Rotate it around the Z axis. Set the angle to 360 divided by 8, then divided by 2. Okay, that looks way better. If you look closely, the spike bases look a little strange here. That's expected. We're approximating a cylinder with an octagonal prism, and the 2 layers are rotated to create a staggered pattern. We'll fix this later. With the first 2 layers done, we'll use rectangular pattern one more time. Copy these 2 bodies upward along the Z-axis. Keep the distribution type set to spacing. Set the distance to layer height. And set the quantity to layer count. Now it's starting to take shape. Let me check the height of the top and bottom surfaces. We've set the height parameter to 60, but the model is measuring 63.75. So let me open the parameter table and see what's going on. It turns out the stagger between the layers is adding an extra half layer. The total number of layers should be the bottom half layer plus the layer count. So the layer height formula should be height divided by layer count plus 0.5. Let's check again. With the layer height parameter fixed, the model matches the 60mm height we defined. At this point, the spikes are done, but we still have a few finishing touches. For example, I'll add another cylinder through the center, create a sketch on the XY plane, draw a circle, hit E to extrude. I'll make it slightly taller than the height parameter so we have enough room to add chamfers on both ends. I used join here, but I actually recommend using new body instead. If you change the height parameter later, the join operation may fail because the number of bodies involved can change. The spike bases looked a little strange before, but adding the center cylinder makes them look much better. Before we wrap up, there are still a few cleanup steps to finish. To make the model look more refined, I'll add a small chamfer to the top and bottom surfaces. This also helps reduce elephant foot during printing. If you want, you can also add a keychain loop at the top. You may also notice that we haven't merged all the separate bodies, but don't worry, this won't affect the print at all. Sending these independent bodies to your printer works perfectly fine, as long as you don't manually split them in the slicer. Now, it's time to see the real magic of parametric modeling. Let's open the parameter table and play around with the values. From here, you can easily change the diameter and height. Everything scales perfectly without breaking a single feature. You can also change spike height. The higher the value, the sharper and more intense it feels. Ouch, that looks painful. This model and the Fusion 360F 3D source file are available on MakerWorld. You are welcome to download and check the source file. Through this file, you can clearly see every step of the modeling and the parameters I've used. Okay, send to print. Here's the final print. This is the low pain version. I think I can handle it. And this is the high pain version. See how different they look? Yeah, I think I can feel phantom pain just looking at it. Oh, that really is painful, but somehow I can't stop playing with it. I could already feel the pain when I removed it from the build plate. The pain level is mainly controlled by the spike height, so you can dial in the level that suits you. To make it more fun, I decided to make a rotating version. Which one should I use? Let's go with the high level one. Create a new plate and copy the model over. First, split the fidget in half. I'll use the default split height. Next, download the rotate joint and socket cutter we created in an earlier video. Drag both of them into the slicer. First, split them into separate objects. The connector is lying on the build plate, so I'll move it off to the side and print it as is. Then use the socket cutter to cut matching holes into the 2 split faces. I'll move quickly here, but you can watch that earlier video for the full explanation. Duplicate the socket cutter because both halves need a hole. Merge the socket cutter with 1/2 of the fidget, align it along the x-axis, then the y-axis. Select the socket cutter and move it along the z-axis until it's in the right position. About here. Okay. Run the Boolean operation and choose subtract. Let's take a look. Yes, the hole is right there. The other side works the same way, just in the opposite direction. First, flip the socket cutter around. Then, merge it with the other half. Center align it. Move the socket cutter up or down until it's at the right height. Finally, run the Boolean subtract operation. As you can see, there's now a hole on the bottom of the other part too. All right, arrange the parts and slice them. Everything looks ready. Send to print. Remove the brim first. This is the connector. Insert it into the socket on one side, then push it into the other side. This part can be a little painful, so it really tests your tolerance. Now the two halves can rotate. However, they don't spin as freely as they could because the two mating surfaces have quite a bit of friction. A little sanding should help. Okay, that's all for today. If you found this tutorial helpful, please hit the like button and subscribe for more 3D printing designs. Let me know in the comments what should I model next. Thanks for watching, and I'll see you in the next one.